Yeah, sorry for trouble. So I'm Masamichi Zaizen from University of Tokyo in Japan. So thank you for organizing excellent symposiums. So now I talk about neutrino flavor convergence in quark supernovae. So this physical is is from quantum nature of neutrinos. Yesterday and today, we had already had very nice lectures and great interesting talks about quark supernovae. So I think we don't have explained the detail about the mechanism of quark supernovae, but key point is the neutrinos can transfer the thermal energies, momentum, and lepton numbers from the hot quarks to the cold storage shock waves. So this means that neutrinos can work as mediators because of the nature of weak interacting particles. And this means neutrino transport is essential in the theoretical predictions of quark supernovae. However, as you know that quark supernovae contains multiple physics, so we have still many obstacles. So one of the uncertainty is neutrino oscillations. This oscillation phenomenon can be seen from the standard solar neutrino problems. Neutrinos in the sun, so neutrinos are emitted from the fusion cores and propagate through the envelope in the sun. During propagations, so these emitted neutrinos have the potential from the background electrons, and the dispersion relations can be modified. From this potential, neutrino flavor is converted to the different ones. For example, in that case, electron neutrinos is converted to the mu and tau neutrinos. So from these oscillation phenomena, so when we observe the electron type neutrinos, the number of the detection is reduced from the predictions. So this is the solution of the solar neutrino problem. And in the case of quark supernovae, we can extend these mechanisms. Now here, so we consider the potential from background electrons. In the case of quark supernovae, we need to consider the neutrinos themselves. Under these high-dense environments, neutrinos themselves can be the potential to the propagating neutrinos. In these descriptions, so neutrinos are emitted from the protoneutron stars, and these neutrinos swim to propagate through the sheath of the leptons and the nucleons. Under these descriptions, so these neutrinos can take the nonlinear effect, and this neutrino-neutrino interaction can change the flavors of neutrinos. And this, the occurrence possibility search has been investigated with the state-of-the-art of quark supernova simulations. So this colored region shows the occurrence regions. And for example, in the top panel, so this colored region is spanned between the 10 to the 10th to the 10 to the 12th gram per cubic centimeters. So this means the neutrino flavor convergence can happen near the protoneutron star surface. On the other hand, in the bottom panel, so this region is slightly less dense from compared to the bottom top ones, but this density region is roughly 10 to the 8 to 9 gram per cubic centimeters, and this means neutrino flavor conversion can occur behind the stored shock waves. This means that neutrino flavor conversion or quantum nature can change the explosion dynamics in quark supernovae. And recently, so some groups have investigated the impact of flavor conversion to the explodabilities. In these simulations, they simply assume the prescriptions. So they assume the neutrinos reaches the flavor equipartitions below the critical densities. And this means after the flavor convergence, so this, in that case, so anti-electron neutrinos and the heavy electronic neutrinos are equilibrated like these ones. And they set the critical densities in parametric ways, I mean by hand. In that case, the shock dynamics can be changed clearly, these ones. So this shows the time evolution of the shock radius, and considering flavor convergence, the onset of the shock revival becomes much earlier. And this is the impact of shock dynamics, but the other simulations reported the impacts on the gravitational wave signals. So for example, in the left one, in the 2D simulations, and the right panel shows a 3D simulation case. In these simulations, so these groups consider the flavor convergence at deep cores. For example, in that case, so 10 to the 13th to 14th gram per cubic centimeters. The other one in the 10 to the 10th to 12 gram per cubic centimeters. From this flavor convergence, shock dynamics and the proto-neutron convections can be clearly changed, and the gravitational wave signals also change. From summarize from these results, we need to consider the neutrino flavor convergence into the quark supernova simulations. Importantly, the typical oscillation length scale of flavor conversion is roughly the scale of 1 centimeter or some centimeters. So direct computation of the neutrino flavor convergence with quark supernovae is computationally impossible. So we need to some modeling. We need some modeling of the flavor conversion is necessary. And to do this, we need to understand the dynamics of neutrino flavor convergence themselves. And usually, to describe the flavor convergence, we write the quantum kinetic equations. So this rho means neutrino density matrix, and this neutrino density matrix contains classical neutrino occupation number distributions. And this Hamiltonian is oscillation Hamiltonian, and this C is a coordinate integral. From these self-interactions, we can find 3 types of flavor instabilities, and these flavor instabilities lead to the nonlinear flavor convergence. So to understand the neutrino flavor convergence, we need to understand these flavor instabilities. And these instabilities are triggered by the asymmetries in the neutrino distribution or neutrino properties. For example, in this one, the asymmetry is neutrino energy. The other one is asymmetry in angular distributions, and another one triggered by the asymmetry in collisions. So now I will focus on these 2 types of instabilities and compute the dynamics of the flavor convergence. So first one, so we focus on these ones. So this is called the first flavor instabilities. And this instability is triggered by the asymmetry in angular distributions. In these regions, so neutrino angular distribution is no longer isotropic, and this angular distribution is forward-peaked structured. So in these instabilities, so angular distribution is crucial. In the context of fast flavor instabilities, we usually employ the ELN minus XLN angular distributions. This ELN means the electron-lepton numbers, and XLN means heavy leptonic neutrinos. So this ELN means nu E minus nu E bar. And this XLN is nu mu minus nu mu bar, or nu tau minus nu tau bar. In the context of quark supernovae, so nu mu is almost identical to nu mu bar. So usually this XLN is 0. So ELN angular distribution is important. And the asymmetry in angular distribution means this ones. For example, so this is angular distributions of electron type neutrinos. And this 1 means the forward direction, and the -1 means the outward directions. And for example, in some angles, anti-electron neutrinos is over electron type neutrinos, while in the other directions, electron neutrinos exceeds over the anti-electron neutrinos. In that case, this instability is triggered. In the context of ELN angular distributions, in some directions, this ELN is positive and the other one is negative. In that case, flavor instability happens. And this is a simulation of the fast flavor convergence. So this bottom panel shows neutrino flavor content. So this red color shows electron type neutrino is dominant. On the other hand, blue one is X type neutrino is dominant. From these numerical simulations, we can find that in the final state, this ELN minus XLN is always positive in the angular distributions. This means this angular distribution is stable to the fast instabilities. So, and importantly, initially in this region is negative, but in the final state, this is almost 0. So this means flavor equipartition is established. So equipartition means electron type and X type is equilibrium. So from these results can be modeled for the fast flavor convergence. And importantly, this angular distribution is not completely equipartition in the whole angular distributions. So this equipartition is only the some angles. So this means realistic simulation shows rich angular structures. So it is not just equipartitions. And here I know that, so this I need to focus on the species. In this flavor convergence, so electron type neutrinos is equilibrated to the muon type neutrinos. And the X and the anti-electron neutrinos is compared to the anti-mu neutrinos, and these two neutrinos are equilibrated. However, in the initial conditions, the electron neutrinos and anti-electron neutrinos is not identical in the Kokoro supernovae. So this mu neutrinos and anti-mu neutrino is not identical in the fast flavor convergence. So this means that if we include or incorporate flavor convergence, so 4 species or 6 species neutrino transport are necessary. So 6 or 5 species is not allowed from the flavor convergence. So this is the one portion of the flavor convergence. And next, I introduce different flavor convergence, and this is called collisional instabilities. And this collisional instabilities is happening between the 10 to the 10th and the 12 grams per cubic centimeters. In these regions, the neutrino distribution is almost isotropic. So this means angular distribution is not very crucial compared to the fast instabilities. But in these dense regions, collisions are important. And the collisions depends on the neutrino energies. So this collisional instability depends on the energy distribution of neutrinos. And importantly, this flavor instabilities happens inside and outside of protoneutron stars. So neutrino reaction also important. Here, I show the two types of flavor convergence. In case ones, I assume that in the number densities, electron neutrinos is dominant over the anti-electron neutrinos. And within and inside the protoneutron stars, electron fraction is roughly 0.1. In these situations, electron neutrinos reaction rate is dominant over the anti-electron neutrinos. In these hierarchies, in the number densities and average reaction rate, we can compute the flavor convergence. In that case, so this result is obtained. This is the time evolution of the transition probability of electron neutrinos. So if this value is zeros, electron neutrinos remain to the electron type, but this is 1, electron type neutrinos is completely converted to the heavy leptonic neutrinos. And clearly we find some, and sorry, I don't mention, so this colored line shows the energy distributions. This red color shows high energy neutrinos. This blue line shows low energy neutrinos. And clearly we find low energy neutrinos beyond the equipartitions. And the high energy neutrinos doesn't show any flavor convergence. It is not equipartitions. And I show the other situations. So hierarchy of number density is the same. However, average reaction rate is twisted. If we consider the electron fraction is roughly 0.5, in that case, due to the averaged energy of anti-electron neutrinos, this hierarchy is switched. In that case, high energy neutrinos goes to the equipartitions. However, low energy neutrinos doesn't show any flavor convergence. So this means that in these situations, neutrino flavor convergence shows a rich spectral structures. It is not just equipartitions. So equipartition assumption is good, but it is still assumptions. So we need to the detailed structure for the neutrino flavor convergence. And finally, I show is feedback to the background matters. So this collisional instability occurs near the neutrino spheres. This means electron type neutrinos is equilibrated with background matters by a beta process. So this feedback effect is important in these regions. And this is the previous result, and we consider the feedback effect in that case. So electron neutrinos, and this panel shows the time evolution of the ratio of the final electron type neutrinos to the initial electron type neutrinos. So in the early phase, due to the flavor convergence, electron type neutrinos is reduced, but feedback from the background matters, so the number of electron type neutrinos is recovered. This means the feedback effect emits the additional neutrino, electron type neutrinos. This means flavor convergence can enhance the cooling efficiency from the protoneutron stars. So this is my summaries and conclusions. So neutrino flavor convergence can change the shock dynamics, neutrino signals, and gravitational wave signals. And currently, we tackle the direct simulation of neutrino flavor convergence, and more accurate modeling of flavor convergence is running. Thank you for listening to my talk.
Very interesting questions. Start here. Thank you very much for the nice note. Sorry.
This one, Tom.
Thank you.
So in previous talk and also other talks, we have heard that neutrino can also contribute to low frequency gravitational wave, right? So in here, if now flavor convergence happens, And also we know that different flavor of neutrino have different mass. So will this also impact on these low frequency neutrino gravitational waves?
For example, in this result, neutrino flavor convergence enhance explosion energy and modifies morphologies. In that case, so neutrino memory effect from the neutrinos happens, for example, in this one and this one.
But are these from matter or from neutrino?
So this is a gravitational wave signal.
I mean, from matter or from neutrino? Because this is high frequency, right? From matter. So my question is the role on the neutrino gravitational wave.
Neutrino. Sorry, I cannot find this. Sorry.
Okay.
Worried about the impact of the neutrino mass itself? No. Because that's tiny compared to the neutrino energies. So it is, maybe I misunderstood your question. Are you worried if you have mixing, of course, it's going to change the populations of your species within your gravitational neutrino low frequency gravitational wave emission. But the neutrino masses themselves, the fact that they're different and you change the populations with those slightly different masses will not impact that, because it, relative to the energy of the neutrinos, it's nothing. Is that what you were asking?
Yeah, very low frequency component will be changed or not, if it's
process of any of that flavor physics has to be energy conserving. So as long as it's just oscillations between different states, anything that feeds into the space-time will remain unaffected. Yes. Right. Yeah. Then Chris and Thomas. No.
Okay, so I had a different topic, which was, so I always thought that we could tell these neutrino flavor oscillations from, they would change the electron fraction and then the yield. How much, what is the effect? Is it detectable, the effect on the yield? Will we get a large effect on the yield from these realistic flavor transformations? Yeah, the nucleosynthetic yield, sorry.
For example, in the final cases, now in this simulation, I stopped the hydrodynamics, but in the realistic situations, so due to these additional emissions, can change the electron fraction of the background matters. So for example, in that case, additionally, electron neutrinos is emitted. So this means the electron is absorbed to the protons. So this enhances the reduction of the electron fractions. So this also can change the nucleosynthesis.
But do you have an estimate on how much it's changing the electron fraction?
Sorry, I don't estimate this one. But in the future, I need to estimate this one.
All right. I think that's probably it. Thank you very much, Masamichi.
Yeah. Thank you for